All right, so that's what Carlos was helping at. So I was reminded that we should clarify that all of our exercises actually use the Atlas meshing library under the hood. So you will not see this as much when you look at the generated code if you are so inclined to look at it, because there it's abstracted away. But for each and every exercise, we link against the Atlas library, and we really use it extensively to make these exercises. So yeah, thanks at this point to all the Atlas developers. But now on to the next exercise. So for this exercise, we want to write a very small solver for diffusion equations. So it's not only going to be a singular operator anymore, but a combination thereof. And something I would like to say right now is that for this solver and the next solver, the methods we are using are of really low order. So we do not claim that they are in any way particularly good, or you should incorporate this into your model code. In fact, please don't. Having put this disclaimer out of the way, here is the equation that we would like to solve. And yeah, you can see here, maybe you already anticipated it, that there is going to be a Laplacian operator on the right-hand side. And the change in temperature is proportional by the diffusivity constant to the current Laplacian of the temperature. So we have two different kinds of derivatives here, right? We have the spatial derivative, which we can attack with an FD or FEM stencil. And we have a temporal derivative, which we are going to feed to a time stepper. And now for the very last exercise, when you were able to reach that far, you computed the vector Laplacian, or rather the vector Laplacian times the edge normal, but still, you computed the vector Laplacian. And now on Cartesian coordinates, the vector Laplacian is simply connected to the normal Laplacian, so to speak, because in this case, the vector Laplacian is just a Laplacian applied to each of the components. So you could express one using the other if you wanted to. But we will not be able to use the approach we did last time. And why? Well, here is something which we didn't talk yet about so far, and we only will briefly brush upon, is how accurate is the stuff we are doing. And for example, one thing which you may have noticed in the last exercise is that the error for the curl was way smaller than the error for the divergence. And this is because the curl formulation that we are using has quadratic convergence, and the formulation for the divergence we are using has only linear convergence. So maybe for the people who are out of the loop, linear convergence means that if you double the number of your elements, you will get half the error. And quadratic convergence means if you double the number of the elements, you will only get 1/4 of the error. So you will have this quadratic relation, which is obviously preferable. So what happens if we look at the vector Laplacian? Well, it turns out that this was a very bad idea. And in fact, if we increase the number of the mesh elements, we will not get an improvement in the error. So the error may be somewhat acceptable on a rough mesh. But if we increase the resolution of our mesh further and further, the error from the vector Laplacian will start to dominate all other errors. And this is obviously a situation that we want to avoid. Okay, so it turns out we cannot use the vector Laplacian formulation which we used in the morning, but we can use another one. For example, we can borrow one from finite differences. For example, the one which we are always showing to you, because this one is simple and it has second order. So here we see this concept illustrated. So here we have the Laplacian, which I'm sure you know by heart by now. However, it's not immediately clear how we would want to do this on FVM mesh, because again, we have not this immediately clear north, south, east, west relations. So how can we do this? And well, here is exactly where the neighbor chain concept is going to help us. For example, we can look at such a piece of our triangular mesh where we have this, I believe in English it's called a diamond. And if we look at the center point of an edge, we basically have just something like a finite difference mesh. We have a left neighbor, a right one. And if we look at the vertices once removed, we also have a top one and a bottom one. And the only thing that's different is that the horizontal and vertical spacings are different, and that's it. So we just need to slightly adapt the formula we had before, and using the neighbor chain concept, we can get a second order accurate Laplacian, which will certainly help us to solve this exercise. Now, if you look at this, you will have noticed that this requires temperature being defined on edges and the temperature being defined on the nodes. So we need to be able to push the temperature from one entity to another. And for this exercise, and I know that's horrible, we are going to do the simplest approach. We're going to do it by averaging. So we are simply going to look at 6 edge neighbors, divide by the cardinality of our neighborhood, which is 6, and end up with our vertex temperature, which we were looking for. Okay, as for the time stepper, we're doing something, not the most simple thing, but a very simple thing. We're going to execute a predictor step in the start. We're going to, so here this is basically building up the ODEs where we put our right-hand side with the Laplacian approximator we just discussed. And at the end, we're going to execute a corrector step. And this actually also goes into the dusk code that you will have to write, because we want to highlight that it's not only like stencils around the space, right? It's also perfectly fine to write a time stepper in dusk and dawn. There will be some boundary conditions to consider. And we're just going to assume that no heat is going to leave the domain. So we're simply going to put the Laplacian to 0 on all edges. Okay, here again you have a reference slide where all variables are explained to you. And one thing I would like to bring to your attention is that for the inverted word and edge length fields, which are supposed to represent these lengths, they have been divided by 1/2 for you. Like you will not need to pull out any factors of these quadratures. So basically, if you divide by these fields, by the square of these fields, you will be fine, and you will get the right result. Okay, that's it. There is going to be hints on the next slide and the slide after. So in this case, I would say, because the exercise is a little bit more complex, if you have very little numerical experience, then maybe look at the first 2 hint slides, because there is a proper skeleton of the whole algorithm on the second hint slide. And well, at the end, sorry, there is, well, let's say a proper outline on the second slide after this, and at the very end there is the code skeleton, which basically gives away a lot. Currently I don't have the schedule on the top of my head, but I believe you have at least 40 minutes to toy with the exercise now. I believe even 50 minutes, after which we have a half-hour break. Would that be right, Carlos?
Yeah, exactly. So the plan or the agenda is to take the coffee break at 3, but of course, I mean, you're welcome to just continue working or go for a coffee break in between, or as you prefer. So I think the point is that we will reconvene in the go-to meeting for further presentations at 3:30. And then until then, we will be on the Slack so people can work on their exercises, go for coffee, and we'll be on the Slack and help everyone.
Yes, that's exactly the plan. So I hope you will have some fun with this exercise, and I hope to meet you on Slack. Again, do not hesitate if you have questions, if you have feedback. We would be very happy to hear from you.